we have two startups here who are going to tell us about their new technologies helping in this process. So first up, we have Meredith Doyle from the National Renewable Energy Lab and the Department of Energy Bottle Consortium. Meredith.
All right, thank you, Kristen. I'm going to share my screen. All right, and thank you all for having me here today. I'm really excited to tell you about this consortium that we stood up about a year ago. We have funding from both the Department of Energy and then also from industry. And we have made a lot of progress in the past year. And I'm excited to tell you a little bit about myself, but most importantly, what Bottle is doing and really the justification behind this and how we really think that we can make a difference in this area. So just really briefly, I wanted to introduce myself. Again, I'm Meredith Doyle. I'm a chemist by training. I've spent the last 10 years in industry, and about 6 months ago, I moved over to NREL to be the Chief Operating Officer for Bottle. Plastic waste is something that's always been really something that's concerning to me, and I've wanted to transition into an area in sustainability that would be making a difference and helping to solve these challenges that our world faces. And so it's really exciting to be a part of a team of scientists that are all really energized and are rallying behind this, and both in the Bottle Consortium and then also in other parts of NREL as well. So it's just a great experience. And with that, I'll start telling you a little bit about why we're doing the Bottle Consortium. And some of this I know that Ben will talk about as well with his water pack project, but just to tee it up a bit here. So on the right, this is showing, yes.
I'm not seeing anything on screen. I don't know if I'm the only one, but you may want to stop sharing and share again.
Okay. Sorry about that.
There we go.
Meredith, we're able to see your screen now. It's when you go into presenter mode that it did not come through.
Interesting. Okay. Well, maybe I'll leave it like this if that's okay for you.
That works.
All right.
Yeah,
okay,
we can see it.
Thank you so much. Awesome. Okay, so again, on the right-hand side of the screen here, it's showing some recently published articles about how plastics pollution is really affecting our environment. And so on the top right here, we're showing how plastic rain is showing up in protected areas of the United States. So plastics are really showing up in the sea and land and in the air, really just in the environment all around us. And so this is really growing to be a problem of epic proportions, and it's something that is really, growing at an alarming rate. On the bottom here, this is also showing how plastic waste is associated with disease in coral reefs in Southeast Asia. I'm sure most of us have seen or heard about these large plastic plumes that are, showing up in our oceans. But this is another way that really plastic in the ocean is starting to affect wildlife on coral reefs as well. Some images in the middle here just showing how plastic is really, showing up on our beaches and in our oceans. And then I also wanted to talk a little bit about how plastic pollution is really not going to get better or is not projected to get better as we get to a later date. So by 2050, we're expected that plastics production is going to increase threefold. And a recent report has shown that the ratio of plastics to fish in the ocean, that plastics by weight are going to exceed the number of fish in the ocean by 2050. So quite an alarming statistic. Also, as of right now, or as of 2014 at least, 6% of our global oil consumption goes to plastics production. However, we can expect this to increase to 20% in 2050. So really, this problem is not going to get better anytime soon. And if we want to, prevent pollution of plastic waste and also deal with this as really what we're seeing as an energy crisis as well. We're using fossil fuels to create plastics. We really need to start coming up with some more sustainable solutions. And so a bit about current recycling approaches, because this is relevant to what we're doing in Bottle. Current plastics, waste management, and recycling approaches are really limited right now. Only about 9% of plastics actually get recycled. And this is a schematic at the bottom left-hand side of the screen showing how plastics get recycled into the different types of plastics in the sorting cabin down below here. But for the most part, plastics get recycled into something that we term more on the downcycling, which is turning into something with less desirable properties than the plastic that it came from the virgin material. Typically, this is done by mechanical recycling. However, mechanical recycling isn't even applicable to all polymers. So even when we do mechanical recycling, we're ending up with polymers with less desirable properties, and then sometimes we can't do it at all. And so in general, there's really little economic incentive for plastics reclamation. It's just easier for industry right now to produce plastics from virgin materials, which is coming from fossil fuels today. And so that brings us to the Bottle Consortium and why we really stood this up. There are, besides the pollution problem, as I talked about, there's really an energy upside to coming up with advanced recycling technologies for plastics as well. And so our vision for Bottle is to deliver selective and scalable technologies that enable cost-effective recycling, upcycling, and increased energy efficiency for plastics. And then the mission is to develop robust processes to upcycle existing waste plastics and to develop new plastics and processes that are recyclable by design. And so on the right-hand side here, the top chart shows how, this is how we have a linear plastics economy today. So typically, fossil fuels are pulled out of the ground and mined, and then at an oil and gas refinery or at a chemical plant, they're turned into monomers, which for those that don't know, monomers are a building block basically to make polymers. So they're shown here as these little orange dots, and they're really just, the chemistry building blocks that turn into polymers. And so, this is how monomers are made, and then they turn into polymers. And then after that, they're turned into their final use product, which are kind of shown here as, some examples being water filters, plastic bags, parts for automobiles. But then after a set time, and this could range, from days to many years, depending on the application, they're disposed of. And, if they don't make it to a recycling plant, there's some options of what's going to happen to that material. One of them is that it'll be burned. And so when this happens, you're taking this energy intensive, plastic material, which has lots of carbon in it, and you're releasing all of that carbon up into the atmosphere and creating greenhouse gases. Not really a great, not really great for the environment, and from an energy perspective as well, because we're releasing all of this energetic material into the environment through greenhouse gases. One other thing that could happen to the plastics is it could be dumped into landfills. This might actually be more of an optimistic reality for plastics, where it will just sit there. But then another option is it could leak. And if it leaks, it's going to end up in the environment, such as our oceans. And so really not a great, not a great end of life situation for plastics currently within our society. So really what we want to do is move from this linear plastics economy to something that's circular. I'll start over here with the product again. So if we can take these products and through advanced recycling means deconstruct them into building blocks, such as these monomers I was talking about. And then we could take these monomers and make them into a polymer again. And when we talk about making them into a polymer again and starting with monomers, we can usually get properties that are really the same as the virgin plastic material, or something that's has really desirable properties, unlike the current technologies used today for recycling, including mechanical recycling technologies. And so if we can enable this, we could really close the loop and enable a circular economy, which would be really advantageous for us. Just wanted to show down here really quickly, Bottle is, it's headed at NREL, but we have 10 partner institutions shown down here. 5 of them are national labs, and then 5 of them are academic institutions. And each brings a really unique skill set to this picture. And it's really the collaboration between each of these 10 institutions that gives Bottle our advantage right now. Okay, and I just wanted to end on this slide here. I know there's a lot of information, but again, just showing that plastic waste, and we're thinking about it in all different types of plastic waste. And we are guided by analysis as well. So looking at what's going to be the most useful in terms of technologies and what's going to be adopted by industry the fastest. And then also what types of plastics are going to be most easily to recycled, and what types of plastic are going to give us the most benefit in energy and pollution. Things like that is what we're looking at when we're deciding what types of projects to look at as part of this consortium. And then, as I talked about before, deconstruction is a main focus as well. So, for example, we are looking at thermal catalysis as a chemical process to decompose plastics. And then we're also looking at other types like biocatalysis. We're really trying to be agnostic here in terms of the process and just do the one that's going to yield the best results and most easily be adopted by industry. And so after decomposing, we're bringing it down to these raw materials or monomer units that we can either turn into an upcycled material. So this is kind of showing 2 different paths here, either upcycling it into something different or turning it into an infinitely recycled polymer. So turning it back into the same exact thing that you started with. And so this would enable what we like to call closed loop recycling. So where, for example, you have a soda bottle and you recycle it and you turn it back into a soda bottle, and you can keep on going infinitely around this closed loop. Another thing that we are really considering here is using biomass instead of fossil fuels, so that we can really have some benefits here in terms of decarbonizing industry as well. But with that, I know I've taken a lot of time here. I can pass it along to Ben, or I can stop for questions. It's up to how you want to do this, Kristen.
Yeah, sure. I'd love to stop for questions. I know I had some questions for you, but I'd love to open it up to the audience in the Q&A for questions. Is there anything in there, Haley?
Not yet. Send in your questions and we'll read them out.
Send in your questions. We're wanting to stop after each presenter to ask questions because I know this is a lot to digest. So we welcome the questions. The one question I had for you, if you could repeat, how much of the global oil production is going to plastics currently?
Currently, let's see if I can get back there. So currently in 2014, it was 6%. It's probably a bit higher right now, but I don't have the exact number. Yeah.
But higher than I would have thought. So interesting.
Yeah.
Thank you. So Phil has a question.
Yes, Phil, do you want to read? Well, do you have an assumption? Okay, you go for it.
Okay, yeah. Do you have an assumption for the price you will pay for your waste plastic feedstock in order to work through then the cost for production of your upcycled material?
Yeah, we do take that into account in our analysis. I don't know off the top of my head. It varies for every type of plastic that we're looking at, and we really go into depth and study, the nitty gritty of each material. But that we definitely take that into consideration with our analysis team. Yeah.
Do you assume that you will get the recycled material that's been the different plastics that have been separated according to their classification?
Yeah, that's a good question as well. We're working with some recyclers, especially some in the area, to analyze what we get out of recycling plants and see what we can work with. We're also working with some industrial partners, so they have different types of supplies in terms of plastics recycling. So, for example, some industries reclaim their materials at end of life. And so that's another thing that we're considering as we go through some of this as well.
Thank you.
All right. Oh, Phil, I'm going to cut you off so we can get to you. Okay. Next up is Ben Moorer. He's the principal investigator for the Water Pact project. Ben, take it away.
Thanks, Kristen. Hopefully you can hear me. And let's see if we can get this to launch here. And if not, I might employ Meredith's strategy. Are you seeing the proper one, or do I need to switch it?
Looks good,
Awesome.
Ben.
All right, great, thanks. So I'm Ben Maurer. I'm the Sustainable Oceans Lead at National Renewable Energy Lab. I'll be telling you today about WaterPact, which is the Waterborne Plastics Assessment Collection Technologies project. It's just getting off the ground with the help of about 30 scientists from across 2 national labs and multiple programs. So we reach into the oceanography parts of the national labs and all the way across to things like Meredith's project with Bottle. It's just getting started. We're just being funded for FY22 after about a year of scoping and prep work. And yeah, very excited to be here today to talk about what we're going to be doing and what sort of opportunities I see in the future there. So I unfortunately get to be the doom and gloom person, I think, for today's panel, beyond what Meredith was saying before. Just to throw some really ugly statistics out there quickly. We leak, if you remember Meredith's diagram, we leak about 1 million metric tons or so of plastics into our watersheds domestically in the US every year. And to visualize about how much that is, that's every trash truck, garbage truck in the United States full of plastic, dumping a full load of plastic into our waterways. We also export about 1 million metric tons of plastic waste to other countries. That becomes a problem in their waste management systems and their watersheds as well. And that plastic is not just ending up in the ocean, it's ending up in the watersheds themselves, it's being deposited in the riverbanks, it's ending up in the ecosystems, and it's ending up in our communities. So even here in the United States, where we have excellent waste management, we are seeing microplastics in our drinking water, we're seeing plastics in our food sources, both aquatic and terrestrial. There are plastics in the deepest parts of the ocean. There's a video of a plastic shopping bag in the bottom of the Marianas Trench. It's at the top of Mount Everest. More local to us here, it's at the top of inaccessible parts of the Rockies. Meredith showed a picture of a study that was done on plastic rainfall, precipitation, and there's precipitation and winds that are carrying plastics up into reaches where people can't actually access themselves. There's a lot that could be done on this, but initially we need to understand what the problem is. And then eventually, after an initial assessment, we'd like to start developing technologies on these 4 pillars. So we've got sensing, collection, conversion, and redesign that a few years from now, we'd like to be addressing this problem head on, leveraging the resources of the national laboratories, the Department of Energy, and our partner agencies in this to start looking at a 20-year outlook on how best to significantly reduce plastics in our waterways and in our ecosystems, and significantly reduce those that we're emitting into the ocean overall. Another depressing statistic, there was a study that came out this year that says we might be the 3rd highest emitter of plastics into the ocean behind India and Indonesia. There was a range on that, but that was the upper range, and it's not a good look, I would say. The way that we're going to start this project out, I mentioned we're going to go out into different watersheds and look at different rivers. We chose, after some initial study, these 5 rivers for the reasons highlighted in blue there. There are a bunch of stats there. Some of these I can tell you off the top are wrong. They've been revised in the last 2 or 3 months. Upwards, there's more plastics than we initially had modeled in that, well, not we, but then the leading scientists who are looking at this had initially modeled in that space. But basically, if you look at the column on the right-hand side, we were looking at a 5-corner look at the US, where we captured a large renewable energy resource that we might pull from the river itself to drive these sorts of technology solutions, a significant flow of water, a bulk of the plastics, so between half and around 3/4 of the plastics that's modeled to be emitted from the US within these rivers. You can see that 1 river is accounting for most of that. And about 1/3 to 1/4 of the population that lives along these watersheds. And the reason we chose these 5 rivers are listed there. The Mississippi is just the 800-pound gorilla in the room. They top the charts, peg the meter on pretty much everything. The Delaware, we actually have some DOE projects through the national labs that will be modeling the complete system, including human effects in the Delaware. It's a $150 million project. I believe it's about to be funded if everything goes well. That's looking at the Delaware watershed all the way out to the coastal sea and the Delaware Bay. And so we'll be piggybacking on the back of that. It's a great opportunity to develop some plastic modules and plastic models there. The Sacramento is a really interesting river. It comes out into the San Francisco Bay where there are a number of reclamation projects already planned for nonprofits that are working in the space. But as a river itself, it goes through a lot of California agricultural areas and then through 2 major urban areas before reaching San Francisco Bay. Those familiar with the Los Angeles quote unquote river know that it's basically a concrete trench. They've filmed car chase scenes through the canal that's in LA there. And so it's a major engineering challenge to uphold those 4 pillars of technology development there, sensing, collection, conversion, and redesign in that sort of environment that's so different than the others there. And then finally, if we're going to leverage the infrastructure that's already there, dams, wastewater treatment plants, combined sewer overflows, then the best place to look is probably the Columbia that has some of the most built out hydropower infrastructure in major urban centers along the Columbia River of any in the US. There are 2 rows on the bottom. Those are our local partners and our, well, along 2 different lines, one for the physics, one for the community outreach there. Those are still being decided. Initially, it looks as though we're going to be able to partner with some sister agencies and have them leverage the expertise they already have in these spaces to go do some of our sampling and community outreach. So there are 4 parts to this assessment. The first part is going out and measuring. There are some really great measurement campaigns that have gone on all over the US, but understanding what plastics are there, what renewable energy resources are there, and how it's affecting the communities is a very specific look, and we'd like to do it across the full spectrum of size, shape, chemistry, and position in the river. And so this will be a study to do this in the exact same way for all 5 rivers and have comparable data at the seasonal high, the seasonal low, and at least 1 flooding event for each of these rivers. And I know it's an eye chart. We can come back to this if folks have specific questions about river plastics or locality data that we intend to gather. But this is a preliminary list of the type of data that we'll be gathering with our partners. And then once we have the plastics, we'll be bringing them back to lab. Bottle will be doing a lot of the analysis work for us. And then there's also a really, I guess, fancy lab that'll be processing the background water samples to be looking at the chemicals that are being leached out of the plastics themselves and ending up in the water. Beyond the field campaign and laboratory analysis, we'd like to extrapolate from those results that will be at 1 location on a river, downstream of an urban center and upstream of the river mouth into the ocean. We'd like to be able to extend those measurement results up and down river. And what you're seeing on the right-hand side there is a video that's made from a computer simulation up in Puget Sound. So it's looking at floating particles that are being discharged from, I believe, the Duwamish River into the Salish Sea there. And you're seeing the back and forth sloshing as the tides affecting the river flow as it comes out into Puget Sound. So this modeling will give us access to better understand what renewable energy resources are there to power these sorts of devices, but it'll also let us have insight into the fate and transport. So the sources, sinks, the transformation and transport of the plastics as they travel downstream. And like I mentioned before, we'll be trying to piggyback on top of existing work in the Delaware River to develop these sorts of models. Central to this project is understanding what the value is. So it's not just the financial value of the plastics as they're put back into the supply chain. That is a big part of it, but it's also the avoided costs in the environment. So on the supply chain side, we have the economic value of the plastics themselves, what's been invested in them so far. We have the carbon that's been emitted to make them, transport them, use them so far, as well as the energy. And then on the cost, the avoided cost side, we have the social, environmental, and the health costs. And again, we'll be partnering closely with Bottle. They've developed a lot of these systems to evaluate this from the terrestrial perspective. And we'll be trying to take those systems and tune them and expand them into the aquatic environment and the near coastal marine environment. Finally, the field campaign, field measurement data, the model data, and the evaluation data we'll be hosting on waterpack.org. And the goal here isn't necessarily to engage the public directly, although that's a secondary goal. The primary goal here is to give accurate, accessible, actionable data 2 stakeholders that are already operating in this space. There's over 105 as of last year, small to medium enterprises working in this space. And we think that we can really help their missions as well as ours by providing them with the data that we're getting. And also in doing so, leverage the data hosting capabilities and the visualization, the power of the computing resources of the national labs to do that in one central location. So an overall view of what we're trying to do here, there's multiple different sources of plastic debris that end up in our watersheds and are washed into the rivers. They come in all sorts of sizes, from nano all the way up to macro. And there's multiple opportunities to understand the problem and to address the problem and return value to the circular economy there. I'll end with this real quick. These are the opportunity areas that I see in the near-term future for innovation and possibly commercialization. They fall into the spaces that really just aren't being addressed, but are resulting in really high costs, I would say, or high leakage of investment to date. So I'll end with there. Welcome any questions, and thanks for your attention.
Great. Thank you, Ben. That's equal parts exhilarating and depressing, right?
Yeah.
I don't see any immediate questions, and we're going to be running short on time. So Phil, why don't we move on to you, please?
Thank you very much. Let's see. See my screen? Now you can. See my screen? Okay, very good.
Yes.
Okay, so hi, I'm Phil Pienkos. I'm the founder and CEO of Polaris Renewables, and I'm also an emeritus scientist at NREL. And I'm very happy to be here today at the Denver Startup Week to talk about Polaris and what we're doing to try and encourage and add to the circular economy. So why am I speaking at the Denver Startup Week when Polaris is located in beautiful Potsdam, New York? Top photo is a picture of the incubator space where Polaris labs are, but this technology grew out of NREL. For the 14 years that I was at NREL, I was the lead of the algal biofuels program. And one of the challenges, as anyone who's involved in biofuel production knows, the challenge is to compete with petroleum-based products on cost. And so the same is true, especially true for algae. And so we were constantly looking for valuable co-products that would scale and that could help drive the economics for biofuel production. And what we came upon was the notion of making non-isocyanate polyurethanes. And I'll talk a little bit more about those, actually a lot more about those. And so I helped invent this technology at NREL, decided to retire from NREL in order to commercialize the technology, and started Polaris last year in order to do that. One of the aspects of the technology that I'm especially proud is that it was recognized with an R&D 100 special award for market disruption last year. So the problem, and we all know about some of the problems in plastic and recycling and upcycling, downcycling, but it's an especially acute problem for the fashion industry. 2.1 billion tons of carbon is emitted by the fashion industry, and 60% of the products that are produced in the fashion industry come from petroleum. And so this is an industry that is simply not sustainable, and they know it. And so Polaris saw this as an opportunity. 90% of consumers, younger consumers, believe that companies have a responsibility to address environmental and social issues. And it's a large market. $1.8 trillion a year worldwide is spent on fashion and footwear. And so in order to meet customer demand and compete in the marketplace, the fashion industry is really looking to increase their sustainability credentials. So the polyurethane market, we have a beachhead market in fashion and footwear. we're looking to, we believe that our technology will most rapidly move into films to be used for waterproofing, synthetic leather, and decoration. But we believe we could quickly move into our serviceable, addressable market, which is much larger. And this includes foams for footwear, apparel, and outdoor gear. Ultimately, if we were successful in developing the technology and getting scale up and getting our costs down, we believe that we could begin to make inroads into the total addressable market, which is $60 billion a year. And this includes other applications like coatings, buildings, automotive, furniture, etc. This is a growing market, and so it represents a continued very lucrative potential for Polaris. So the solution is that Polaris has developed non-isocyanate polyurethanes, or NIPUs. And I don't really want to go into the technology a lot, except to point out that Polaris begins with triglycerides, and these can come from algae, though also from terrestrial crops like soybean oil or linseed oil. Linseed is our favorite. Also could come from waste streams like yellow grease or brown grease. One of the things we worked on that I especially like is the opportunity to remove oils from spent coffee grounds and use those for fuels or for polyurethanes. One of the part of our technology that I really want to highlight is that we take the double bonds that are present in fatty acids in our lipid streams. We convert those to epoxy groups. And then our unique chemistry allows us to react these epoxy groups with CO2 to form these bicarbonate rings. These cyclic carbonates can be reacted with bio-based amines to form our bio-based non-isocyanate polyurethanes. So this gives us a significant impact in terms of carbon footprint. If we simply remove the isocyanates and replace it with our technology, we can see a 33% reduction in the carbon footprint. That's because we're using bio-based feedstocks, but also that we have the CO2 incorporated directly into our product. As it's been noted, a lot of polymers don't make their way, aren't recycled. Polyurethanes is one of those. As a result, polyurethanes tend to accumulate in the environment, but our polyurethanes are biodegradable. That's good, but it still means we're only borrowing CO2 from the atmosphere, and we're going to put it back into the atmosphere eventually. And so the notions that Meredith talked about to be able to recycle, break down, and upcycle into new products is one of our goals. We have a business-to-business model. Our partners are the fashion brands, and we've talked to a lot of these brands, including companies like Adidas, Patagonia, and Allbirds. We see the fashion brands as our partners, and we were working with them to go upstream and talk to their polymer suppliers like Covestro, Merrimack, Dow, and Lubrizol, because ultimately for our technology to be successful, if I don't want to build my own polyurethane factories, and I want to be able to work with the suppliers to adopt our technology and supply that to their customers. Our go-to-market strategy involves product development in 2021, prototype testing in 2023, and then positioning for exit in 2025. Our strategy is to secure non-dilutive funds for generation of preliminary data, then move to scale up development of our minimum viable prototype for piloting in 2023, place samples into the hands of our customers, and use this time to expand our IP portfolio. Then finally, move to validate our market tech and sustainability data, and to then market our tech for licensing and or acquisition. Our fundraising strategy involves non-dilutive funding We're writing lots of phase 1 STTR grants right now, applying to other opportunities for non-dilutive funding like fellowships, Shell Game Changer, and the Wells Fargo IN2 program, providing complementary work on our minimum viable prototype, and then to go to phase 2 STTR grants in order to build our pilot programs. But along the way, we are constantly reviewing our strategy to allow us to pivot for equity investment when that's warranted. I've been involved in a couple of accelerator programs in 2020, worked with Fashion for Good, which provided very great mentoring and also access to the fashion brands. This year, I've been working with Venture for Climate Tech, more mentoring, access to investors, access to entrepreneurs, and pre-seed funding, which has been critical for moving the technology forward. My team includes my colleague from NREL, Tao Dong, also bringing in our product success manager from in the name of Ben Galfin, a former Patagonia employee who is now has his own consulting firm called Outsider Innovation. I'm also working with the local community and Clarkson University, working with Devin Shipp as a technical advisor, who was part of the team for developing the technology with the funding that we're getting in the STTR proposals. We have a couple of patents through NREL. One has just been awarded for novel NIPU formulations. We have another patent pending for the production of NIPU foams. And Polaris has an option for an exclusive license from NREL for the production and finishing of textiles, athletic apparel, and non-durable household goods. We're building a patent portfolio based on new composition of matter patents. So that's my story. This is where I can be reached. Always glad to talk to people about the technology and to look for potential investment opportunities and partnerships. So thank you very much.
Great. Thank you, Phil. Very interesting. We're going to move right into our next session. Myra Arshad is going to present to us from Alt Tex. Myra, you're on. Go ahead.
Awesome. Sounds great. I will go ahead and share my screen as well. Okay. All right, and you all can see the full screen version of that on your end?
Yes.
Okay, great. So hi everyone, I'm Myra. I'm the co-founder of Alt Tex. We're actually a Toronto-based biomaterial startup, and we're actually creating a more circular alternative to polyester that's re-engineered from food waste. So it's been really great hearing about all of the other fantastic organizations here, and it's actually very interesting that we kind of bring an element of each of those. So Meredith explained very well the issue with petroleum and the use of plastics. Ben talked a little bit about the issues of microplastic pollution and way more than that. But and then also Philip shared the issue of plastic in the fashion ecosystem. So they teed me up very well. I'll tell you a little bit about how we are trying to overcome some of those issues. So as you already heard today, fashion is one of the most polluting industries on the planet. More specifically, though, the largest and most polluting subsector of fashion manufacturing is actually polyester. So it's something that's found in 65% of our closets right now, and it's this petroleum plastic-based material that creates 7 million annual tons of landfill waste, 40 trillion ocean microplastics a year. Once again, metrics that you've already heard from Ben, Meredith, and Philip. And despite the rise of conscious consumerism, where 60% of young consumers have indicated a willingness to pay a premium for the clothes we wear, polyester is still that subsector, despite being the largest, is the one that lacks fully circular, biodegradable, or recyclable alternatives because of its very specific durability and performance requirements that have made it difficult to replicate in existing bioplastic technology. So at Alt Tex, we're trying to create what we believe to be the world's most circular polyester alternative, created from one of the world's largest landfill contributors, which is food waste. So our three-stage waste to wardrobe solution begins with large-scale post-industrial food waste that is currently being sent to landfill by food manufacturers. We take their food waste and put it through a patent-pending fermentation process that takes the sugars found in the food waste and ferments them, resulting in a biofiber. And that fiber is specifically designed to fit into the existing manufacturing system of the polyester manufacturing industry, to be woven into polyester-like materials for use by fashion brands. So double clicking into our technology and our IP a little bit further and talking more about how we're going from waste to wardrobe. The first step of our process involves, once again, taking the sugars, which are abundantly found in food waste, and combining them with a novel combination of microbes and enzymes that create a bioplastic. Bioplastics in and of themselves, the ones that are on the industry today, are not suitable for textile manufacturing because they lack thermal resistance, strength, and flexibility, largely speaking. They lack a few other things, but these are the three main metrics that we then improve through a combination of chemical and mechanical procedures, once again, a part of our IP that optimizes each of these three metrics. So, let me click that. What you get at the end of that process is a polyester-like resin that once again works with existing polyester machinery to be melted and extruded into filaments. And those fibers are then twisted and converted into yarns, where they then once again fit into the textile manufacturing industry to be woven and sewn into the garments that we wear today. So the result of this process is a material that mimics polyester's properties, but does so in a far more circular way, is industrially biodegradable and carbon neutral as well, due to the very carbon intensive waste source we're diverting from landfills. We also project and see this technology being economical and cost competitive because we figured out how to plug into polyester's existing supply chain, and also because we're using a low cost feedstock as input. So moving over to what matters most and the environmental impact we foresee this material having. So we project the environmental impact of a single t-shirt created using this material to divert 1 kilogram of food waste from landfills, 9 kilograms of carbon emissions from the atmosphere, and up to 4 grams of microplastics from polluting the ocean. As I'll get to, we're quite early in this process and still are working with the right agencies to get a lot of our life cycle analysis vetted so we can start communicating and marketing this to customers, but this is what we're projecting for the near future. And here's why that's really important. So as you heard a lot about today, plastic, governments across the world and people across the world are realizing the issue with plastics, and governments are starting to ban plastics and single-use plastics. That flip hasn't switched for consumers to realize that 60% of what we wear is actually made of plastic. And when that flip switches, we will need more polyester alternatives. We've already seen shifts in the industry where 1/3 of the industry has signed the Fashion Pact, committing to 0 carbon emissions by 2050, yet no carbon neutral polyester solution even exists. Once again, being tied together by the fact that the majority of consumers, 60% of them, are willing to pay 20% or more premium for the clothes we wear, recognizing the true cost of sustainable and ethical fashion. Okay, jumping quickly to the business model. I know we're tight on time, so I'll just zip through this. Here's how we get this fiber technology to retail shelves. So fabrics are ordered directly by fashion brands who place an order. $15 a yard is kind of where we're projecting our initial cost to be, and we're confident at larger scale we can bring that down a little bit further. When the order is placed, the fibers that Alt Tex will manufacture in-house are then contracted out to our partner textile mills that then weave those fibers into the appropriate fabric. That fabric is then sent to the garment facility of the fashion brand where it's sewn into the appropriate garment, and the garment is then sold through the fashion brand with the appropriate made with Alt Tex signage, similar to made with Gore-Tex or Intel inside. We have strategic investment from investors who are some of the largest textile manufacturers in the world to ensure that this contracted part is happening with ethical and sustainable textile mills that are being traced. Okay, I'll spend a quick second on this. So competitively speaking, here's who else is on the market and how we are iterating beyond the current innovation. So the biggest alternative on the market right now is this middle kind of bucket of competitors you see here. These are folks who are creating polyester alternatives using largely post-consumer plastic material. So recycled water bottles, for instance. Although they match the quality and durability of polyester, they still have a gap on the sustainability spectrum because that fabric still continues to create microplastic pollution. And it also is not, it cannot biodegrade and is not easily recyclable. In the second bucket, the regenerated fabrics are materials that are bio-based, but they aren't emulating polyester specifically. So they're creating viscose-like material, silk-like material, but not catering to polyester's performance. So we combine the performance of the former bucket with the circularity of the latter bucket to create a polyester alternative that does not compromise circularity or performance. Okay, so wrapping up here, we have a long way ahead of us. We are a seed stage startup. At this stage, we have completed our fiber prototypes, which are patent pending. We have about $1.5 million in funding from private equity and some government grants. We also have letters of intent or pilot agreements with fashion brands for our 2022-2023 launch. And we've also secured food waste contracts with large food manufacturers to produce at least 500,000 meters of fabric. So to that end, here's the team behind Alt Tex. I started the company about 2 years ago to continue my family's history in the textile manufacturing space. My background is in sales and marketing with previous startup experience, and my co-founders here have a combined 13 years of experience in the technology that we're building, and we're supported from advisors, by advisors from industry like Country, Lululemon, as well as thought leaders in the science space. So I will stop there. Again, I know we're tight on time, but thank you very much. Happy to answer any questions.
All right, we have time for maybe everyone's short little snippet on this question. What can we do in our own communities to reduce the waste of plastic and dispose of it in a way that's eco-friendly? And I know Philip already answered it in text form, but just if you want to say it again for the group, that would be great too.
Well, I think the best way to dispose of things in an eco-friendly fashion is not to dispose of them, to use as little plastic as possible, reuse it as much as possible before recycle, and then to demand that the people you buy products from use more and more eco-friendly materials.
Yeah, and I'll just underscore what Phil said. I mean, I think that's right on. There's a great page that the EPA maintains under their Trash-Free Waters program. I put a link to it in the question there that has a list, including links of things that you can do at the consumer level. But like Phil said, there's a whole bunch of extended producer responsibility that probably needs to happen. I mean, it's very difficult, for example, to buy groceries without having some sort of involvement with a disposable plastic. And the good news is that those manufacturers and those agricultural producers, suppliers are taking that on. They're trying to come up with solutions themselves and try to find ways, in that example, to recycle the PET clamshells that you get your berries in, for example. So there's good news on both fronts, but it's not just on the consumer's shoulders.
Anybody else want to chime in on that question? What can we do in our own communities to reduce waste of plastic and dispose of it in a way that is eco-friendly?
Yeah, I absolutely agree with everything Phil and Ben have said. It's just, you know, it's so hard right now. And plastic. Let me also say that plastics have really revolutionized our life. I mean, there are, you know, I don't think any of us are proposing completely getting rid of plastics. I mean, they, you know, cause medical miracles to happen, and you know, food waste to be, you know, lessened, and there's lots of great things that come out of plastics. It's just that we really need to figure out better ways to deal with it.
Yep, I would agree with all that. I also just noticed as I was doing that I was eating and then my microphone was up here. So hopefully you guys actually heard my presentation. And
Oh,
hopefully
yeah.
you can hear me a bit better now. Sorry about that. Yes, I would just echo what Philip said is use less. That's the biggest issue with the fashion industry is fast fashion. We consume way more than we need to. If you use less, you dispose of less.
Okay, we have one more question. Steve H., who's made a couple of comments, have been great regarding microplastics. Is there a known and simply unscaled technical solution for removing them from the water, or is this pretty much an unsolved problem?
And that one sounds like a question for me. It's pretty much an unsolved problem, unfortunately. So most of the solutions that are out there that you'd be familiar with, Mr. Trash Wheel, the Ocean Cleanups, Interceptor, a bunch of NOAA and EPA projects like CBIN is another one, I guess. Those are typically looking at plastics above a 0.5 centimeter in characteristic length and floating. And so the outstanding questions are, how do you get mid-water column and buried in the sediment microplastics that are smaller than a 0.5 centimeter out without damaging the other life that exists there? And it's very much an open question. There are some preliminary, really interesting technologies. Some of them are pretty science fiction, but for the most part, nothing's reached a level where it could be scaled.
So it sounds like we've got some work to do. I want to thank the panelists. This is an outstanding group of people working together here. Meredith, Ben, Philip, and Myra. And I want to thank Haley Whitaker for helping to moderate today as well. And thank you everybody for attending, and we'll see you next time.
Thanks
Thanks
very
a lot.
much.
It's great to be here.
Thanks all.
Bye-bye.